Hi, I'm Michael Pfeifer. This is another episode of Metal Conversations. In this episode, I have a couple examples of failure analysis and root cause analysis projects that I've worked on. Failure analysis is part of the root cause analysis process. We need data from a failure analysis to help understand what happened metallurgically to a metal item. It could be a part in a valve, a spring, an axle, any component from a piece of equipment. And without the information from a failure analysis, it's pretty hard to get to the root cause, and really you're just guessing and wasting time. Sometimes what I see happening is that people will have a failure and spend their time sitting in a room looking at the failed part and try to guess as to what happened. And you really just need to go ahead and do the failure analysis. There are two broad sets of circumstances when a failure analysis is performed. The first is when there's a problem in an engineering company. This is a company that designs and manufactures a product. And they may have either a product that failed or a quality problem with their manufacturing line. And they need to determine the root cause of the problem and in order to prevent it from reoccurring and to fix it. The second set of broad set of circumstances is with insurance companies and attorneys. In many cases, when a product fails, there can be a loss associated with that failure. So, for example, if an electrical appliance causes a fire, then the fire causes damage to a building or a home, or if a piece of plumbing breaks or leaks, then there can be water damage to a home or a building. Or if a piece of equipment breaks and malfunctions and it ends up hurting somebody, let's say, for example, if a crane falls and hits somebody, it may kill them or just hurt them. And in either case, the insurance companies for the people who have gotten hurt, whether it's the building that's gotten on fire or had the water leak or a person that's gotten killed, the insurance company has to make a payment to those people to cover them for the loss. And then they want to go after the party who is determined is at the root cause of the loss for reimbursement. So they want to get compensation for that loss. So that's called subrogation, and so that's its own separate reason for why people do a failure analysis. I've talked a lot in other podcasts and articles about the failure analysis process, so I won't talk about that here. You can go to my website and look at our blogs or podcasts to learn more about the failure analysis process. And also we offer a course on failure analysis too, if you want to learn more about doing failure analysis. Today I have two examples of failure analysis. One is for a company where there's a problem with their manufacturing line, and the other is for an insurance problem. The first example is a company that was manufacturing bowls out of sheet metal, out of steel specifically. What they were doing is taking circular sheets of steel and putting them inside of a press, and there were two metal dies that were in the shape of a bowl would come together, and they would press the sheet into a bowl. And then it would go for subsequent processing. The bowl would get painted, and then the paint would dry. And what was happening is that occasionally they would have a problem which is called orange peel. Orange peel is a cosmetic defect. The surface of the metal has the appearance of an orange. That's why it's called orange peel. This is an intermittent problem. Orange peel is associated with having large grains in the metal. For any particular amount of deformation of a metal, there's a maximum grain size above which we start to see the orange peel. As long as the grains are small enough, we don't see the orange peel. So working with this client, what I did is I got samples of bowls that had orange peel and bowls that did not have orange peel, and took samples of each bowl in the same location, and then cross-sectioned them and looked at the grain structure. What I saw was that the grains in the bowl that had the problem, there were large grains at the surface and smaller grains below the surface. And in the good bowl, there were just small grains throughout. Now, the only thing that affects the grain size is the processing that's done at the steel mill for this steel that was being used. With this information about the grain size, my client went and talked to the steel mill, and they looked into it and found that their process of cooling the steel after an annealing process had malfunctioned, and the steel was not cooled quickly enough after the annealing process, and that enabled the grains to grow large at the surface. So the root cause of that problem was a malfunction at the steel mill. Now, the material still met the mechanical requirements that my client had specified, and it also met the chemical requirements. So it had the right composition, and the material had the right tensile properties. So part of the blame kind of also rests with my client, because they did not specify the grain size of the material. They just let the mill provide whatever they wanted to provide as long as it met the composition and mechanical properties. So we got samples of material from different lots of steel and measured the grain size and determined what the maximum grain size could be before they got orange peel. And they put that in their specifications so that they can then hold the steel mills accountable for providing material that met their requirements. So that's an example of using failure analysis to get at the root cause of a problem and then finding a solution to the root cause to prevent the problem from recurring. The next example I have is with an insurance situation. This is a situation where a water faucet leaked over a weekend in a building, and it caused over $100,000 in water damages. I was hired by the insurance company for the building to figure out the root cause of the leak. So in the previous example, I got samples of the steel and then submitted it to the lab for doing analysis, and the lab just worked the analysis in with their normal flow of material. So we got the results in about 5 days. In a case where it's an insurance company going after other insurance companies, we often have what's called joint exams, where several metallurgists getting together, the metallurgists representing different parties that can be involved in the loss. So it could have the manufacturer of a product as well as the installer, someone who repaired it, did repairs or maintenance on it, and other people that might be involved, and as well as the metallurgist for the company seeking compensation. So in this case, when we have a joint exam, everyone meets at the lab at one time, and we take over the lab and we do all the testing in one day. The thing with this approach is we get all the data quickly, but it costs a lot more because we're taking over the lab for a day. So it can be 2 or 3 times the expense compared to just sending the material to a lab. So in this case, the metallurgist representing the faucet manufacturer and I met at the lab, and we conducted a joint exam. We went through the process of looking at the faucet. We discovered that there was a slow leak from inside of the faucet for water getting outside of the faucet. And that was just a trickle. That was not the problem. But the problem with that slow leak is that it was leaking onto an aluminum nut that was holding the cartridge down inside of the valve. The cartridge is what controls the flow of the water past the valve. The problem is that the aluminum nut was getting wet from the water that was leaking by, and the aluminum was in contact with the brass portion of the valve, which is a problem because that's 2 dissimilar metals in contact, and that was a place where galvanic corrosion could occur, and it did occur. The aluminum nut corroded to the point where it lost strength and it could no longer hold the valve down. The nut broke, and so it could no longer hold the cartridge in place, so the cartridge was pushed out of the valve by the water pressure, and then water at full pressure was able to leak out of the valve because there was nothing keeping the water in. So the metallurgical cause of the problem was galvanic corrosion, and the root cause of the problem was actually poor design. I mean, there are many books that say that we should not put aluminum in contact with brass when there can be a chance of them being in contact with water. They may have thought, well, geez, we're never going to get a leak and that water's never going to get on aluminum, but I think that's a pretty risky thing, putting aluminum in contact with brass in an environment where there is going to be water. The other thing I wanted to say is that these joint exams are not at all like the CSI shows that are on TV. These exams can be tedious, slow going. We have to think through evaluations we want to do, and as we get information, we may change our minds, and everyone has to agree on it. People take their time taking pictures. of the item that failed. And we have just wait around waiting for samples to be prepared. And then when we finally get the data that may indicate the problem, no one rushes out to go after the bad guy. People just calmly in the room collecting data and then going back and writing a report based on their data or talking to their client about the data. To me, the most exciting part about the failure analysis is planning it out and then using the data to figure out what happened metallurgically and then working with the client to then apply that information to figure out the root cause of the problem and help them solve that root cause of that problem. When we do that, that's a very gratifying feeling to me. So that's it for this episode. If you're interested in learning more about failure analysis, go to the Industrial Metallurgist website and look for the blog articles and podcasts on that topic. And as I said, we also offer a course, Metal Failure Analysis, that explains about the failure analysis process, the analysis equipment that are used, and how the tools are used for analysis of fractures, corrosion failures, and production quality problems. So that's it. And also, if you haven't already, subscribe to the Metal Conversations podcast series to receive alerts when new podcasts are released. Subscribe on Spotify, Google Podcasts, Apple Podcasts, and the number of other venues that offer podcasts. Thanks again for listening. Good luck with your metals. Bye.